Hello, everyone. Welcome to this session on digital to analog, DAC, and analog to digital, ADC, converters to critical components in modern signal processing and electronic systems. In today's interconnected world, these converters form the backbone of communication, control systems, multimedia processing, and countless other applications. From converting a music file into sound waves in a speaker to digitizing images for processing in AI systems, DACs and ADCs are essential in bridging the gap between the digital and analog worlds. One of the most critical functions in signal processing is the conversion between analog and digital signals. This process enables efficient storage, processing, and transmission of signals. In the typical signal processing flow, analog input, a continuous time signal, example, voltage or current, is the starting point. Then, analog to digital conversion, ADC, the analog signal is sampled and quantized into a digital format, allowing it to be represented as discrete values. Then, digital processing. The digital signal is processed using algorithms to achieve tasks such as filtering, compression, or enhancement. Then, digital to analog conversion. DAC, the processed digital signal is converted back into an analog format for real-world applications like audio playback or communication. This block diagram ensures seamless interaction between real-world analog signals and the powerful capabilities of digital systems. The figure demonstrates how a continuous time signal, analog signal, is sampled to produce a discrete time signal. Analog or continuous time signal, this signal varies continuously over time and is defined at every point in time. Examples include natural signals like sound waves or voltage. Sampling process. The analog signal is sampled at regular intervals with a period t. This process captures the signal's value at specific time points while ignoring the values in between. Discrete time signal. See, the result of sampling is a discrete time signal, where the signal is defined only at the sampled time points t is equal to nt, nz, but its amplitude can still vary continuously. ADCs and DACs, both types of converters, typically include several essential elements. Comparators. These are used to compare input voltages and play a critical role in the conversion process. Digital circuitry. This processes the signals and manages the conversion logic. Switches. These control the flow of signals within the circuit. Integrators. These are used in certain types of converters to perform mathematical integration of input signals. Sample and hold circuits. These capture and hold the input signal at a specific moment in time for accurate conversion. Passive components, such as resistors and capacitors, which help in signal processing. Finally, a precise voltage reference is crucial for ensuring accurate conversions. The figure illustrates the role of digital to analog converters, DACs, in data systems. The input to a DAC is a digital word composed of parallel binary signals, typically originating from a digital signal processing system. These binary signals are converted into a corresponding analog signal through a process that involves scaling a reference value. The resulting analog output signal may undergo additional processing, such as filtering or amplification, before being delivered to an analog signal processing system. While DAC outputs can be in the form of either voltage or current, the majority of DACs are designed to produce voltage outputs. The digital word is often synchronously clocked. In such cases, latches are required to temporarily hold the word for conversion, and a sample and hold circuit is necessary at the output. This illustrates the fundamental components and operation of a digital to analog converter, DAC. At its core, the DAC takes a digital word consisting of n bits labeled as B0, B1, B2, Bn2, Bn1, and combines it with a reference voltage VREF to produce an analog output. Each bit in the digital word has a specific significance. B0 is the most significant bit, MSB, which contributes the highest weight to the output, while Bn1 is the least significant bit, LSB, contributing the smallest weight. These bits, represented as coefficients, can only take binary values of 0 or 1. The analog output voltage, VOUT, is computed using a scaling factor K, the reference voltage VREF, and the value of the digital word D. The relationship can be expressed mathematically as VOUT is equal to KVREFD, where D represents the combined contribution of all the bits in the digital word. The total number of bits, N, determines the resolution of the DAC, with more bits allowing for finer granularity in the output signal. By using these equations and concepts, the slide encapsulates how digital signals are transformed into precise analog outputs, showcasing the critical role of scaling, bit coefficients, and the reference voltage in this process. This explanation ties together the components and their functionality, highlighting how the DAC bridges the gap between digital and analog systems. By using these equations and concepts, the slide encapsulates how digital signals are transformed into precise analog outputs, showcasing the critical role of scaling, bit coefficients, and the reference voltage in this process. This explanation ties together the components and their functionality, highlighting how the DAC bridges the gap between digital and analog systems. This highlights the basic structure of a DAC, as shown in figure, which includes binary switches, a scaling network, and an output amplifier. The binary switches and scaling mechanisms network interact with the reference voltage to produce a scaled output based on the digital word. The scaling can be achieved through voltage, current, or charge scaling. The output amplifier then boosts the scaled signal to the desired level while also providing the ability to source or sink current into the load. Together, these components ensure accurate conversion of digital inputs into a reliable analog output. This slide explains the fundamental characteristics of a digital-to-analog converter, DAC, which can be classified into static and dynamic properties. The resolution of a DAC, a key static property, is determined by the number of bits in the digital input word and is expressed as N bits, where N represents the total number of bits. To illustrate this, figure depicts the input-output characteristics of an ideal 3-bit DAC, where N is equal to 3. In this case, the DAC can generate 8 unique analog output voltages, each corresponding to one of the 8 possible digital input combinations. These output levels are evenly spaced and separated by the least significant bit, or LSB. The LSB represents the smallest voltage step the DAC can produce, and its value is determined mathematically using the given equation. This precise relationship between the input digital word and the output analog voltage highlights the accuracy and resolution of the DAC. The LSB value is VREF divided by 2 to the power n. This slide explains the fundamental characteristics of a digital-to-analog converter, DAC, which can be classified into static and dynamic properties. The resolution of a DAC, a key static property, is determined by the number of bits in the digital input word and is expressed as N bits, where N represents the total number of bits. To illustrate this, figure depicts the input-output characteristics of an ideal 3-bit DAC, where N is equal to 3. In this case, the DAC can generate 8 unique analog output voltages, each corresponding to one of the 8 possible digital input combinations. These output levels are evenly spaced and separated by the least significant bit, or LSB. The LSB represents the smallest voltage step the DAC can produce, and its value is determined mathematically using the given equation. This precise relationship between the input digital word and the output analog voltage highlights the accuracy and resolution of the DAC. The LSB value is VREF divided by 2 to the power n. In this, let us see how the output of an ideal DAC changes as the digital input increases. For every 1-bit increase in the digital word, the DAC output rises by 1 LSB, demonstrating the stepwise nature of the digital-to-analog conversion process. For instance, when the digital input is 000, the output voltage is 0.0625 V. It is important to note that the output characteristic cannot be shifted downward by a half LSB, as shown by the dashed line, which corresponds to an output of 0 V for the digital input of 000. Since the DAC has finite resolution, such as 3 bits in the example provided, the maximum analog output voltage does not equal the reference voltage V. This limitation arises due to the discrete levels defined by the digital input. To quantify this, the concept of full-scale Fs value is introduced. The Fs value is defined as the difference between the analog output corresponding to the largest digital word, such as 1111, and the analog output for the smallest digital word, which is 0000. This characteristic highlights the inherent constraints of DACs in achieving continuous analog outputs, with the Fs value serving as a critical parameter to describe their performance. The full-scale Fs of a DAC defines the difference between the analog output for the largest digital input and the smallest digital input. This definition remains valid even if the output characteristic shifts vertically by plus or minus 0.5 LSB. In Fig, the full scale is 0.875 times ref, representing the analog output for the maximum input. The full-scale range FSR is the total difference between the maximum and minimum analog outputs, indicating the DAC's complete output span. Both Fs and FSR are crucial for understanding the DAC's performance and output limits. Refer DAC Part 2 video for completing the discussions on DAC.